In this video, we are going to solve topical paper 2 questions that have been randomly selected from two topics from the atomic structure and mass spectrometer and the molar gas volume. Now, before we continue, I would like to appreciate those of you who have subscribed to our channel, and for those of you who have not subscribed to our channel, I will keep on repeating that we are not asking you to donate or to buy pamphlets. We are more interested in your success. Therefore, what we want you to do is subscribe, like our videos, and share to other fellow learners. Thank you. Let's get started. We will be starting with question number 1. Look here to calculate the relative atomic mass of neon. Either you can say 88 times 20 plus 22 times 12 divided by what? Divided by 100. Or you say 88 times 20, 88 over 100 times 20 plus 12 over 100 times 22. And you add up, you have the same thing. It will give you the same figure. So either you say 88 over 100 times 20 plus 12 over 100 times, and you have the same answer. So that is how you can calculate the relative atomic mass of an element given the relative abundance in percentages, and the isotopic masses. Okay, let's move to question number 2. Question number 2, we are now moving into the molar gas volumes. What volume of oxygen at standard temperature and pressure is required for the complete combustion of 1 mole of methane? 2. What volume of oxygen at standard temperature and pressure is required for the complete combustion of 1 mole of hydrogen? Then the molar volume of a gas at standard temperature and pressure is 22,400. And the molar volume of a gas at room temperature and pressure is 24,000 or 24 dm³. So now we have been asked at standard temperature and pressure. So what do? The first thing you do in such a thing is write the equation. If you need to, this is stoichiometry. If you need to calculate the amount of what has reacted with the other one, the first thing you need to write a complete balance equation. So if you write a balance combustion equation between methane and oxygen, what you are going to have will be carbon dioxide and water. Then from the equation you can say 2 moles of oxygen are reacting with 1 mole of methane. Or you can say 2 moles of oxygen are required for complete combustion of 1 mole of methane. From the equation, if there are 2 moles there, remember the volume of oxygen will be what? What will be the volume of oxygen? If 1 mole of a gas at standard temperature and pressure will contain 22,400, then the number of moles there are 2. Then 2 times 22,400 will be what? because the volume we're given here, 22, is for 1 mole. That is 22,400 cm cube or 22.4 dm cube per mole. So if there are 2 moles, what do you expect? It's times 2. And you have 44,800 or 44.8 dm cube or cubic decimeter. So that leads on to question number 3. The second part of the question of hydrogen. The same thing goes with hydrogen. The same thing goes with hydrogen. From the equation, if 1 mole of oxygen required for the complete combustion of 2 moles of is required for the complete combustion of 2 moles of hydrogen, then 1 mole of oxygen is required for complete combustion of oxygen. Then you should know that therefore X moles of oxygen will be required for complete combustion of 1 mole of hydrogen. Because we said for 1 mole. Therefore 1 mole of hydrogen, how many moles of oxygen is required? The moles of oxygen required will be 0.05 times will be 0.05 moles of oxygen. We divide by 2. That is just the moles of oxygen that you have got. Then we need to multiply it by what? 22 times 22,400 in order to have for the one for standard temperature and pressure. So question number 3. If 0.5 gram of hydrogen are exploded in air, which mass of water is formed? Simple. It's very, very simple. Which mass of water is formed? And I told you, if you want to succeed in chemistry and have, especially in stoichiometry, a balanced equation is very, very important. Because when you have a balanced equation, everything you can use, you apply your balanced equation, everything will be okay. Okay, now hydrogen is exploded in air. That is what? That is with oxygen. Now 2 moles of water are formed. 2 moles of hydrogen are used up. So from the equation, we will say now. That from the equation if 4 grams of hydrogen can produce 36 grams of water. If 4 grams of hydrogen, because it is 2. Hydrogen has a mass of what? Times 2. Hydrogen has a mass of the mass of hydrogen. If you look at the mass of hydrogen from from the book of data, the mass of hydrogen has a mass of a mass of 1. Yeah. So from the equation, if 4 grams of hydrogen, why do I say it is 4? The relative atomic number of hydrogen is 1. And there are 2 molecules, and there's 1 molecule of hydrogen there. So 1 times 2 is what? It is 2. Then 2 times 2 is what? It is 4. So 1 times 2, 2 atoms of hydrogen, we will have 2. Times the number of moles. There are what? 2 moles there. We'll get 4. Now there are 4 grams now. There are 4 grams involved. So if 4 grams of hydrogen can produce 36 grams of water, water is 18. 18 times 2 is 36. So if 4 grams of hydrogen can produce 36 grams of water, then 0.5 gram of hydrogen that was given will produce a certain amount of water, and we'll look for X, then it will be 4.5 gram of water that will be produced if 0.5 gram of hydrogen are exploded in air. So that is how you can calculate it. Now, question number 4. A certain container has 17.75 gram of chlorine gas. Calculate the number of atoms of chlorine. The number of atoms of chlorine. The number of molecules of chlorine. We have given chlorine, the relative atomic mass of chlorine to be 35.5. Then the Avogadro constant to be 6.02 times 10 to the 23rd. Remember that atoms, they say number of atoms of chlorine. We are not going to use, chlorine is a diatomic, but we are not going to use it because they have mentioned what? Atoms. Atoms of chlorine. So now, as they have used the number of atoms of chlorine, we are going to use what? We are going to use the number of moles of chlorine will be what? It will be 17.75 divided by 35.5 gram per mole. That is the relative atomic mass for chlorine, 35.5 gram per mole. If we divide that, we'll have 0.5 mole. But remember that the Avogadro constant, this number, is contained in 1 mole of every substance. In 1 mole of, let me say 1 mole of chlorine, 1 mole of iodine, it must be 1 mole. 1 mole of any specific substance will contain this number and will contain specified particles. Could be this number, atoms, molecules, ions, electrons. So in this case, we are looking for atoms that are present in 17.75 gram of chlorine. So in that case, we are not going to, since chlorine is diatomic, we are not going to multiply 35.5 times 2 because we have been asked to look for the number of atoms. Since we have been asked to look for the number of atoms, we are going to use only 35.5. So 17.75 divided by 35.5 will have 0.5. And since it is stated that 1 mole of every substance will contain 6.02 times 10 to the 23rd atoms, 1 mole will contain 6.02 times 10 to the 23rd atoms. Therefore, 0.5 moles will contain what? With just a matter of multiplication. 0.5 times 6.02 times 10 to the 23rd atoms. You will have 3.02 times 10 to the 23rd atoms of chlorine. That's all. Then again, calculate the number of molecules of chlorine. Okay. See the difference? Chlorine is diatomic. This is where we have to use the Cl2 now. This is where we have to use Cl2. Still using 17.75. In order to have the number of moles in the molecule of chlorine in Cl2 this time around, it will be 17.75 divided by the molar mass of chlorine molecule. That is Cl2. It will be 35.5 times 2. We are dealing with molecule now. 35.5 times 2, and that will give us 35.5 times 2. Then you divide 17.75 by 35.5 times 2. You have the number of moles this time around. To have the number of moles of the chlorine molecule, it will be 17.75 divided by 71 gram per mole, and it will be 0.25 mole. Then the number of molecules in this number of moles are how many? It will be what? since one mole of every substance will contain 6.02 times 10 to the 23rd molecules, then 0.25 will contain what? Will be 0.25 times 6.02 times 10 to the 23rd, and we will have 1.505 times 10 to the 23rd molecules. That is how you get such an answer. It drives us to the next question. A volatile liquid is composed of carbon and hydrogen in the ratio 1 mole of carbon and 2 moles of hydrogen. That is 1:2. 0.124 gram of liquid on evaporation at 100 degrees Celsius, and 1 atmosphere gave rise to 45 cm3 of vapor. Calculate the molecular mass, or the molar mass, then calculate the molecular formula. In order to have the molecular mass or the molar mass, you need to use the ideal gas equation, which is PV equals to nRT. And we can calculate for N as the number of moles. There's one thing, you can calculate for N. You can calculate for N as a number of, method number 1, you can calculate PV equals to nRT. You can make N the subject, which N is the number of moles. Then the subject will be PV divided by RT. That's method number 1. And then you have the number of moles. Since the molar mass is mass divided by number of moles, this mass that has been given here, we will divide it by those number of moles that we have got. We will have the same molar mass. Method number 2, you can still use PV equals to, instead of using N, you use small m and divided by capital M. Small m represent the mass, capital M represent the molar mass, RT. Then we will make capital M the subject, which is the molar mass, and then it will be mRT divided by PV. Then we will do our conversion. Especially for temperature. Only for temperature we'll do our conversion. Only for temperature this time around. We'll add 273 there to degree Kelvin. Then again, we will also for volume, volume, we will divide volume by volume by 1000. So we are going to change degree Celsius to Kelvin by adding 273, and we will change the volume from cubic centimeter to cubic decimeter by dividing it by 1000. Then we substitute in the equation that we have got, small m times capital R times capital T divided by PV. When we do that, we will have our molar mass to be 84. That will be the molecular mass. Then we were told carbon and hydrogen exist in the ratio 1:2. Then calculate the molecular formula. Remember that when you have this, already have the molecular mass, it is very easy. So we now say it is now the CH2 that we were told is an empirical formula. That is the empirical formula. The carbon C and the hydrogen H2. Now that is an empirical formula. An empirical formula times a certain number X will give us the molecular mass. So now, we now say carbon has atomic number of 12. That is 12 times X will be 12X. Then hydrogen has 1. 1 times 2 is 2. 2 times X is 2X. Equals to what? Equals to 84. 84 now, it will be 14X. Now the value of X will be 6. Now we now substitute the value of X into CX H2X. We now have C6 H 6 times 2 H12 hexane. That will be the molecular formula. the molecular formula of our compound. Just like that. Let's proceed. Identify M. M is rubidium. And which group of the periodic table rubidium belongs to group 1 of the periodic table? It belongs to group 1. It belongs to group 1 of the periodic table. It belongs to group 1 of the periodic table. So some of these questions are very, very trickish. You must know how you can solve them. Write your equation. Balance the equation first well. Then use the information that you have been given and arrive at what is, and give what the examiner wants from you. It takes us to the second part of it. A hydrated salt. We have a hydrated salt there. It is Al2SO4 3X water. That is hydrated aluminum sulfate. Contain 8.1% of aluminum by mass. Find the value of X and give the new formula for the salt. The new formula is, when we find X, we replace X with a formula, with a number, and that will be the formula. So what is happening here is that you have been given a certain number, you have been given a certain percentage. So what you need to do here is, the molar mass of the hydrated salt is what? Aluminum is 27 times 2 plus SO4 times 3 plus water is 18 gram times X, that is plus 18X. Now, it gives us 342 plus X. We stand it there. But remember that they said contains 8.1% of aluminum by mass. So in this case, you need to look for 8.1%, that is 8.1 all over 100. 8.1 all over 100 times what? Times that amount that we were given, equals to what? Equal to the aluminum. Again, 8.1 all over 100 times the molar mass, equals to aluminum as Al2 mass, the Al2 mass. So now when we figure out that and do the manipulation, we will have 2770.2.145.8x equals to 5,400. And by solving it, our value of X will be 18. So by replacing 18 on the X with 18, our new formula now will be Al2SO4 in bracket 3 18H2O. That is it. It takes us to the next question on the polarizing power of cations and the anions. The polarizing power of cations and the anions. Now, arrange the following ions in a decreasing power of polarizing state in a decreasing power, that is from the highest to the lowest. Starting with the highest, explain why it is so. We have been given the cations and we have been given the anions. Okay, for the cations, we have the answer is beryllium, magnesium, calcium, copper, and we ended with lithium. Why do we start like that? We said for a cation to have a high polarizing power, it must have a high charge and a small size. High charge and a small size. Beryllium, magnesium, calcium, all of them, and copper, they have the same charge. In terms of sizes, beryllium is the smallest, followed by magnesium, calcium, and the copper. And the last one is lithium. It has a very small size, and again, it has a very small charge. That is how the answer comes. Then with anions. For anions, we will start with the one that has a high charge and a high size, a big size. For them to have a high polarizing power, it is different. They have a high charge and a large size. So among all, oxygen has a high charge. Even though it has a high charge, even though magnesium, iodine, and chlorine, they have more than oxygen, but when we start with the charge is given the preference first before the size. It has a high charge, so it's given the preference. Then among other ones, all of them have only one a charge of -1. But in terms of sizes, iodine has the highest, followed by chlorine, and lastly by fluorine. So that is the whole thing. Now we go to the next one. Briefly describe how you would measure the first ionization energy of an element. You look at the mass spectrometer, you'll be able to figure out what is happening there. Your knowledge of the mass spectrometer will give you how you can describe how the first ionization energy of an element can be measured. For instance, when the cathode is heated from the supply of voltage, electrons are emitted from its surface. These electrons fall on a grid which is positive, and there is a flow of current in the grid circuit. These electrons bombard with the atoms of the noble gases as they stream from the cathode towards the grid. As the PD between the cathode and the grid increases, there is acceleration of electrons through a valve at a greater speed. Increase in the voltage between the cathode and the grid increases the kinetic energy of the bombarding electrons. The kinetic energy of the bombarding electrons, which is just sufficient to ionize the gaseous atoms inside the valve, can be determined through the voltage across the grid, the cathode and the grid, since K is equals to EV. It takes us to the next question. Briefly state and explain. Briefly state and describe what happens at the position A to F in the diagram above. What are the uses of a mass spectrometer? Yeah, you see this. You see that at A, we'll call it says state. When they say state, you just place the vaporization. Then you cannot describe. You can explain. At A, there's vaporization. Molecules in a sample are vaporized to form gaseous atom. That is, they are converted to the gaseous phase by heating. At the point B, there is ionization. Gaseous atoms of the element in the vaporized sample are converted into ions. At the point C, there is acceleration of positive ions. The positive ions are then accelerated towards the negative plate, with lighter ones accelerated most. At the point D, there is deflection of ions. Ions are deflected by the magnetic field, and ions with high charge and a small mass are deflected most. Then E, ion dictator. There's ion dictator at E. The stream of ion is brought to a dictator after being deflected by a strong magnetic field. The ions of heavier and heavier isotopes are brought to the dictator ion. To the dictator ion. F. At F, the dictator is connected to a computer which displays the mass spectrum. Anything that comes there is displayed, displays the mass spectrum there. You now see it through the computer, where there are peaks and where there are no peaks. Note, the mass spectrum produced, for the purpose of revision, the mass spectrum produced shows the relative abundance, that is isotopic abundance, on the vertical axis, that is on the y-axis, and the mass to ion charge ratio on the horizontal, that is on the x-axis. It takes us to the next question. which is, okay, the uses of the mass spectrometer. The mass spectrometer, you should know that the mass spectrometer is an important device that is very, very important in analytical chemistry. It is used to determine the relative isotopic mass of any substance. It is used to determine the relative abundance of isotopes. It is used to determine the relative atomic mass. It is used to determine the relative molecular mass. And it is also used to determine the structure of compounds. The structure of compound we see are determined by the mass spectrometer. The last section, the mass spectrum of a vaporized sample of chromium shows the following data. We have the mass of the isotope, 50, 52, 53, 54. The relative abundance, 0.04, 0.84, 0.1, 0.08, 0.02. Calculate the relative atomic mass of chromium. Yeah, that was last year question. You'll see that it is very simple, as I told you. You will just multiply 50 times 0.04 plus 52 times 0.84 plus 53 times 0.1 plus 54 times 0.02, and then divide it by sum of relative abundance. The relative abundance is what? 0.04 plus 0.84 plus 0.1 plus 0.2, and which is 1. And therefore, what will be the relative atomic mass of chromium? Sorry, the relative atomic mass of chromium will be 52.06 AMU, that is atomic mass unit. Thank you for listening. I just want to remind you, for those of you who have not subscribed to my channel, that we are more interested in your success, and in return, what we want from you is that you should subscribe to our channel, like our videos, and share to fellow users. Thank you once more.